So this is it. This is the last topic of our chemistry GCSE, and it's on fertilizers. It's a natural extension of the Haber process, as we'll hopefully see. So this is a list of the things that we're expected to know. If you look at the command words at the start of the sentences, describe, recall, state, so they are fairly straightforward, or they should be fairly straightforward things for us to get our heads around. We've got the one at the end which says compare the industrial production of fertilizers with laboratory preparations. So again, we'll make a comparison of those things, but it's not too difficult. So NPK fertilizers hark back a little to topic 8 when we talked about formulations. So the first thing I'd like you to just think about is what exactly is a formulation, or how did we describe it back then? It's a formulation. These are formulations that contain nitrogen, phosphorus and potassium. Those are the three elements that we're really interested in, and as was sort of alluded to in the production of ammonia, the impact it's had. One of the key areas has been fertilizers. You can see that nitrogen is present in these fertilizers, but plants also need other minerals as well, and they need phosphorus and they need potassium. If you look at the bag in the bottom right hand corner, it says NPK fertilizers 5, 10, 15. You could think about, just before we have a look, about what those numbers might represent. So I'll just let you maybe pause the video or think about that for a second. So remember, a formulation is a mixture, but it's a mixture in which everything has been added for a particular purpose and precise quantities are measured. So we see that a lot in drugs. So if you buy an ibuprofen tablet, it'll be 200 milligrams of ibuprofen, but the tablet itself will be more than 200 milligrams, and all of the other ingredients will have been added to serve some purpose, whether it was to make the tablet easier to swallow or to make the ibuprofen easier to digest or whatever. But they're deliberate mixtures. So those numbers on the bag that we've got in the bottom right, they are to show either the ratio or the percentage of each of those three elements that we have in an NPK fertilizer: the nitrogen, the phosphorus, the potassium. Not all plants need the same quantities of each, so you may choose a different fertilizer for a different crop or a different plant. So here are just some real life examples. We've got a starter fertilizer, a high quality fertilizer, different fertilizer, but you can see there are different ratios of the three elements. The key thing about, one of the key things about a fertilizer also is it must be soluble, because you want it to be able to leach into the ground. You want the roots of the plant to be able to take up and absorb the nitrogen and the phosphorus and the potassium. Obviously it's there to help crops grow, and as we've already said, you would have different formulations for different crops. So again, they are deliberate ratios that have been developed with particular needs in mind. So I think we can probably begin to understand why we might follow Haber process with NPK fertilizers, given that ammonia is going to be one of the sources for the nitrogen in an NPK fertilizer. So connections are sometimes made between the production of ammonia and subsequent questions about NPK fertilizers being produced. And going all the way back to C4, or chemical changes, remember we did reactions of acids, and one of the things about ammonia is that it's a base, and then it can react with an acid to make a salt. So really what we're interested in are the salts, because salts are, generally speaking, water soluble. All ammonium salts are water soluble. All nitrates are water soluble. So if we make ammonium nitrate, we've got now a source of nitrogen, a salt that can dissolve if it rains or when it rains, or we can dissolve it straight into water and spray the fertilizer over the crops. We get a neutralization reaction. Ammonia plus nitric acid produces ammonium nitrate. And we've also now got a compound that has two sources of nitrogen, the ammonium and the nitrate. If you remember earlier on, we looked at the checklist for this topic, and one of the things that we had to do was compare the production of nitrogen-containing compounds, either in the lab or industrially. So if we think about industrial, that's not something we're terribly familiar with, but it would be carried out. We've got these giant vats, we've got high concentrations, very exothermic reaction. We can produce a lot of the compound quite quickly. In the laboratory, we would be able to do it using something that you did as a core practical in for the paper 1 side of the course, which was a titration, and then a crystallization. So actually, that's almost like a combination of, well, it is a combination of 2 of the core practicals you did. You made a soluble salt, crystals of a soluble salt, and you did a titration. And titration allows us to be much more accurate and to be careful in the quantities that we use, and obviously the crystallization is a way of getting the final product at the end. So I just want you to think about the steps you would need to take to perform a titration. So in effect, actually, this is asking you, what is the method? This is a core practical question. What is the method for a titration? So just pause the video and have a think about that before we look at the answer to that. So we're going to have the acid or the alkali in the burette, and we're going to have the other in a conical flask. So let's assume that we put the acid in the burette and we put the alkali in the flask. So here we've got ammonia and we've got nitric acid. The conical flask, whatever's in the conical flask, we will have measured using ideally a pipette. I know it's got a measuring cylinder in this picture, but actually a pipette would be much more accurate. We would add an indicator to that conical flask. You do not have to name an indicator. In fact, I would strongly argue that you don't name an indicator, really, because then you don't run the risk of saying something incorrect in terms of the colour change. And what you most certainly must not add is universal indicator. You're going to have a white tile under the flask so that we can see any change in the indicator much more clearly. You're going to add the acid to the conical flask. Remember, the conical flask in my example here has got ammonia in it. You've got to add it slowly and really towards the end point, and the end point is the point of neutralization. You're going to add it very slowly, so drop-wise, okay? Drop-wise. As you add the acid to the alkali, you should be swirling it and mixing it to ensure that all of the reactant mixes with, well, all of the reactants mix, sorry. And then you're looking for a color change. And the moment you have the color change in the indicator, or the indicator changes color, that is your end point. That is when you stop the titration. If you were looking at the results for this, then you would be measuring the difference between the initial reading and the final reading. So you might not have started your burette at 0, you might have started at, say, 1.0, and you may have, at the final reading, may have been 26.0. I'm just deliberately picking easy numbers here. And the actual titra, the actual volume that you'd added, would have been the difference between 1 and 26. So that would be 25.0. So you'd make a record of that. And if you were doing this, if you were doing a titration to work out the concentration of something, you would be making sure that you got concordant results. So you would repeat the titration until you got results that were 0.1 centimetre cubed within each other, and then you would take a mean of those concordant results, of those results that are 0.1 centimetres cubed within each other. So we've neutralised our ammonia in our flask. We've basically added the exactly right proportions of ammonia and nitric acid to each other. So we want to form the crystals of the salt, which will be ammonium nitrate. So remember, we're transferring the solution to an evaporating dish. We are going to gently heat that evaporating dish. We're going to do it until the solution becomes saturated. The way that we know that the solution is saturated is we're looking for the appearance of crystals around the edge of the basin, or where they at the edge of the solution in the basin. So just where the solution edge is, when we begin to see crystals forming just at that edge, we know that we now have a saturated solution. Saturated solution means that no more solute could dissolve in that solution, so it's having to precipitate essentially. They're going to take it off the heat because we want it to evaporate, the remaining water to evaporate slowly. That's going to give us much better crystals. So we would then let the solution cool, the crystals will form, and eventually all of the water will evaporate and we will left just with the crystals. Just to make sure, we would filter them and we would leave them to dry in a warm place, just to ensure that all of the water was now removed. So just have a read through of these subsequent questions about, well, the first one, the reactants in the laboratory at a much lower concentration than in industry. So what impact do you think this would have on the temperature of the reaction, and why do you think that? And also, why couldn't crystallization be used in industry, do you not think? So think about the steps that we've just followed and why that may be a problem in industry. So obviously it's a human being performing the titration method, so we have to think about safety. How exothermic the reaction is going to be proportional to the concentration essentially of the reactants. So if we don't have the concentration too high, we won't get such an exothermic reaction happening during the course of the titration, and so it can happen in a much more sort of safe environment. The problem with crystallization in industry is that it is so slow. You need to let that water evaporate slowly to get the good crystals, and so that just isn't a feasible process in industry. Okay, so we can really break down these fertilizers into, well, they're all salts, but we can break them down into three. So some of them are mined, so you have to be aware of the ones that can be mined. So we've got here potassium chloride and potassium sulfate. So we would literally be able to dig those out of the ground. And some of them are made by reacting acids with bases. So we're going to start by looking at phosphate rock. This is something that we can dig out the ground. We can react it with nitric acid. That will give us two products. It'll give us phosphoric acid, which we can use in a subsequent reaction, and it gives us calcium nitrate. The phosphoric acid that we've just made, we can react with the phosphate rock, so to get a triple phosphate, what's called as a triple superphosphate, sorry, and that is essentially calcium phosphate that we've produced there. And then finally, we can react the phosphate rock with sulfuric acid. That'll give us something called a single superphosphate, which is a mixture of calcium phosphate and calcium sulfate. So reacting phosphate rock with nitric acid, with phosphoric acid, with sulfuric acid can give us salts that contain nitrogen and phosphorus. Focus more specifically on nitrogen-containing compounds, then ammonia is going to be something that we react with the three main acids, the nitric acid, sulfuric acid, and phosphoric acid. So remember, this is a neutralization reaction. Ammonia is a base. So if we react ammonia with phosphoric acid, we get ammonium phosphate. If we react it with sulfuric acid, we get ammonium sulfate. And if we react it with nitric acid, we get ammonium nitrate. So remember, phosphoric acids give us phosphates, sulfuric acids give us sulfates, and nitric acid give us nitrates. And that's it. That's the end of the course. That's the end of the GCSE. Congratulations. You've been brilliant. Really, really brilliant. And wow, amazing, eh?